Okay, welcome back to another video of equivalent series. Right now, today we are going to see how equivalent heat conductivity is solved. Equivalent heat conductivity. Right. So we have heat conductivity in the last part of thermal physics. Right. Heat conduction and heat conductivity. Right. So basically, if I quickly recall the theory part involved here is for equivalent for heat conductivity. Right. Before the equivalent. This is the equation of heat conductivity, right? And equation is for the amount of heat flow. Equation is for the amount of heat flow, right? Now, if we have a rod of length L, see length L, sorry, cross-sectional area A, where it carries a heat flow of Q over T, and it should be well lagged, right? So like this, the system should be well lagged, as there's no heat loss to the environment, right? And to have an axial heat flow, right? So if yes, the valid equation is Q over T equals Ka theta 1 minus theta 2 over L, right? Theta 1 is temperature at this end, theta 2 is temperature at the other end, and always heat flows from high temperature to low temperature only, right? This is the relevant theory part here, and this is valid for rods. This is valid for rods, right? Rods. But when it comes to questions, this is applicable for any other kind of like same shaped materials, like across a wall, across a wooden block, rods, right? Maybe some kind of a substance layer, for anything that is applicable. Basically, now I have written this equation for a rod, right? Now let's see the series combination of rods and parallel combination of rods in heat conductivity, right? Okay, first series combination. See, first on series combination. Right? Series combinations are end-to-end connections. Then one rod to the other rod should be connected as end-to-end connection like this, right? End-to-end. Then see, say I have two rods like this. I have two rods like this, and we'll consider their area as A, right? And lengths as equal L and L. Let's consider equal lengths L and L for the ease of calculation. Otherwise, if lengths are different also, still you can do the calculation and get an answer. Now this is for the ease of calculation. Let's say K, heat conductivity, right? Heat conductivity of these two rods are K1 and K2. Heat conductivities of these two rods are K1 and K2. K1, K2, right? And heat flow which flows through the system is Q over T, right? Now, if the system is well lagged like this, if the system is well lagged, see, if the system is well lagged, there's nowhere other than flowing through the rod for the heat. There's nowhere to go other than flowing through the rod, right? And it's an axial flow. It's an axial flow, right? So therefore, if same Q over T, if Q over T comes in, same Q over T flows through this one, the other rod, and goes out from the other end. So therefore, first idea is Q over T, rate of heat flow, Q over T, rate of heat flow is same, is constant in a series combination of rods. Q over T is constant, right? Now, if this is the resultant, the equivalent, right? Equivalent should be the single rod to replace these two. Single rod to replace these two. And I told you in the previous video also, if there is the equivalent should be doing the same thing which was doing by the system single-handedly, right? And it should be able to replace the system as a single unit. Therefore, it should match the same gap that we have used the system, right? So therefore, now this system was between these two ends now. Single equivalent should also be between the same ends with the same length. So therefore, length of this equivalent should be 2L. Length of the equivalent should be 2L, but area is same A. Since this carries a heat of Q over T, rate of heat flow of Q over T, this should also carry the same rate Q over T. Right? This should also carry the same rate Q over T. Now, let's say these temperatures are theta 1, theta 2, and intermediate temperature theta naught. Now here this is connected between theta 1 and theta 2. Right? The system is connected between temperatures theta 1 and theta 2. Then this single rod, equivalent rod, should also be between theta 1 and theta 2. Same temperature difference. Right? Then let's consider this K as Ke. This K as Ke. Right? In the previous video also I explained you that always if you have a different physical quantity, you have to build up the argument for that different physical quantity. Build up your argument for the different quantity. Now, Q over T is same, right? But temperature differences are different. Can you see? In the first one, temperature difference is theta 1 minus theta naught. In the second round, temperature difference is theta naught minus theta 2. Temperature differences are different, right? So therefore, I'm going to approach with temperature difference here. So when we deal with temperature difference, especially in heat conductivity equation, in series combination, it is easier when we can, if you can, subject temperature difference from the equation. See, now this is the equation we have. Q over T equals, see, Ka delta theta over d, theta 1 minus theta 2, delta theta over d, right? So I'm going to subject delta theta from the equation. Then it is Q over T times d over Ka, right? Q over T times d over Ka. Now, what I'm going to do is, I'm going to apply this equation separately for these three rods, right? Delta theta for the first one. See, now for these three rods, we are applying this. For the first one, delta theta is theta 1 minus theta naught. Theta 1 minus theta naught equals Q over T. Length is L over K1A. Right? I'll refer this equation as equation 1. Similarly, do the same for second rod. Temperature difference is high temperature, low temperature, right? Always heat flows from high to low temperatures. Theta naught minus theta 2 equals same Q over T flows L K2A. We'll consider this as equation 2, right? And then I'm going to apply this again for the equivalent. Theta 1 minus theta 2. Theta 1 minus theta 2 equals same Q over T flows. Right? But length is 2L KEA. Right? Here I have another equation, let's say equation 3. Right? Now here my approach is this. I need to cancel theta naught. Therefore, first I'm going to add these two. 1 plus 2. Right? 1 plus 2. See, look at the result. Here I'll be adding 1 plus 2. 1 plus 2. What happens? When 1 and 2 is added, theta naught 2, theta naught cancels. Then only theta 1 minus theta 2 remains. Theta 1 minus theta 2 remains. From this remaining part, Q over T L over A is common. Q over T L over A is common. Then what is remaining? 1 over K1 plus 1 over K2. Right? Now, can you notice that this is also theta 1 minus theta 2. And here also I have theta 1 minus theta 2. Then I can do a plug-in, a substitution for theta 1 minus theta 2 from here. See, from here I can plug that value. For theta 1 minus theta 2, this can be written. Look at the simplification. Q over T, now from this side, Q over T, L over A, 1 over K1 plus 1 over K2 equals, from here, Q over T, 2L, KEA. Q over T2, Q over T cancels. L2, A2, L2, A cancels. Right? Now, subject Ke from this. To subject Ke, apply a common denominator. This will be K1 plus K2 over K1, K2 equals here 2 over Ke. 2 over Ke. I'll be writing the final answer here. Subject Ke. So Ke equals 2K1, K2, 2K1, K2 over K1 plus K2. This is called the equivalent heat conductivity in series combination. Equivalent heat conductivity in series combination, right? So if there are three rods, this equation is going to be different as how? Here it will be 1 over k1 plus 1 over k2 plus 1 over k3, no? And here 3 comes. Then here it will be not just k1 plus k2 plus k3, then it is going to be k1 k2 plus k2 k3 plus k1 k3 over k1 k2 k3. So therefore, when it comes to this equation, it's always better if you can do the simplification and get it done, because this is unlike the equations we have put for springs and resistors and capacitors, right? Now here the behavior is a little bit different, right? This is only for two rods. This is only for two rods in series combination, right? K equals 2k1 k2 over k1 plus k2, right? Now this is the series combination. Now let's see what happens in the parallel combination. Parallel combination. Okay. Parallel combination, right? Now in parallel combination, let's consider two rods which are in parallel combination like this. See, let's consider two rods which are in parallel combination like this, right? And the area is A of each and length is L, right? Say temperature difference is theta 1 and theta 2. And it carries a heat flow of Q over T, the system. System carries a heat flow of Q over T, right? Now, temperature difference are same, right? Compare these terms. Q over T is given for the system. And from the equation, we know Q over T equals Ka delta theta over D, you know, right? K is different. Let's say K1 and K2. K1 and K2, K1, K2. K is different. But A is same, right? Delta theta is same. D is also same. Therefore, for sure, Q over T is going to be different. Did you get my point? Because Q over T is Ka delta theta over D, you know, right? Now, A is constant. Delta theta is constant. D is constant. Then, when K is different, according to K, Q over T should be different. So, therefore, different Q over T is going to flow in parallel combination. Different Q over T, different rates of heat flow is in parallel combination, right? So, let's consider this as Q over T 1, and let's consider this as Q over T 2, right? Now, as a system, again, same Q over T should come out, but on the rods, inside the rods, in the rods, Q over T is different, right? Okay, now the equivalent to replace this system is equivalent to replace the system is now the system had an area of 2A because A and with the length L. Therefore, equivalent should be doing the same thing single-handedly. Then it should have an area of 2A single-handedly, right? That is important. This is the equivalent with an area 2A but the same length. Area should be 2A, right? And it should carry the same Q over T which was carried by the system, right? And same Q over T. Temperature difference should also be same, theta 1 and theta 2, right? Okay, let's consider this as Ke. Now, argument is straightforward. Different physical quantity here is Q over T. Write the equation, develop your argument for different quantity Q over T, right? Then total Q over T should be, see, total Q over T should be Q over T 1 plus Q over T 2, right? So we know Q over T can be expanded using this equation. And this is the equivalent side, Ke, not A 2A, Ke 2A, delta theta is theta 1 minus theta 2 over L, right? For Q over T1, K1, A, theta 1 minus theta 2 over L. for Q over D2, K2 A theta 1 minus theta 2 over L, right? A2 A cancels. This whole bracket theta 1 minus theta 2 over L2, theta 1 minus theta 2 over L2, theta 1 minus theta 2 over L cancels, right? So what's remaining? 2KE equals K1 plus K2. We need KE. KE is K1 plus K2 over 2. This is the equivalent heat conductivity in parallel combination. Equivalent heat conductivity in parallel combination, right? So as a summary, in series combination, Q over D is equal, but temperature differences are different. In parallel combination, temperature differences are same, but Q over Ds are different, right? Exactly opposite. Okay, so hope it's clear. I'll stop this video here. See you all in the next video with another equivalent. Goodbye.